The damped oscillator consists of a mass or a box with mass m, which is attached to a spring of spring constant k and experiences some sort of fluid friction. Sometimes we can illustrate that by using a dash pot, or we could imagine that it's the air resistance, or maybe the box itself is oscillating in oil or some other kind of fluid. Anyways, there's a fluid friction characterized by a parameter p, and the k is the spring constant. It has units of newtons per meter, so it's a force per meter, and the fluid friction parameter has units of Newton times second per meter. So what we're going to do to solve this problem is to state Newton's second law, and before we do that we need to choose a coordinate system, and here we will choose a coordinate system which is at the center of mass of the box here, and has a horizontal and a vertical x and y axis. That's because the forces work in those directions, so that's the most convenient coordinate system we can choose. And I'm assuming that the box is in neutral position here. That means the spring is neither compressed or stretched at this position here. In the y direction, the vertical direction, there will be a gravitational force here on the box, m times g, and there will be a normal force pointing the opposite direction. In the horizontal direction, there will be a spring force. I'll just draw it this way, but actually it may be the other way. That depends on the position of the box. Let's just call it F spring. And then there is a friction force. I'll use another color for that. And in fact, that force might also point in the other direction. That depends on the velocity, the direction of the movement of the box. So let's try to state Newton's second law. And before we do that, and I'll do it in the x direction because that's the direction of interest here, let's just remind ourselves what those forces, how those forces behave. Well, the spring force is minus k times the position of the box. Why is that? Well, the position represents the deformation of the spring. If I stretch the spring, the position of the box will be at a positive x coordinate. Let's say here, if I stretch the spring, I pull the box out so that the center of mass moves over here. X becomes a positive number, and the force, the spring force, is then a negative number, meaning that it works in the opposite, in the negative x direction. If I push the box so that I compress the spring, so I move the box so that the center of mass is now over here, then the x coordinate of the box becomes negative, and so the spring force will become positive due to this minus here. So the spring works to push back the box. So it always tries to move the box back to neutral position. That's how the spring works. For the friction force, let's write that like this. It's almost the same, except it works opposite the movement of the box. It tries to dampen the movement of the box. So if the box is moving in this positive x direction, the friction force will be in the opposite, in the negative x direction, trying to oppose the movement. It doesn't matter if the box is on the negative or the positive part of the x-axis. What matters is the direction in which it moves, and that's why the friction force here depends on velocity, not position. So it's a v here for velocity. Now, velocity is the same as position differentiated with respect to time. So let's just remind ourselves that. And now we're ready to state Newton's second law. The mass times the acceleration in the x direction, that's what we're talking about here, is equal to the sum of the forces in the x direction. So what that amounts to is, well, we have the spring force and the friction force. The normal force and the gravity here don't work in the x direction. They only work in the y direction, so we don't have to include them since we're projecting the forces onto the x-axis. And when we project the normal force and the gravitational force onto the x-axis, they just become points, so they don't have any magnitude. Right. So we insert the expressions. This one for the spring. This is, by the way, Hooke's law. And for the friction force. And then now's the time to remind ourselves that acceleration is actually the derivative of the velocity with respect to time, which is again the second derivative of position with respect to time. So we can rewrite this, like that, obtaining this expression, which is indeed a differential equation. If we rearrange, we get something like, how we put the equation into standard form, and now it's easy to see that it's a homogeneous equation. It's second order, and it's linear, and it has constant coefficients. This is actually a type of equation that we can solve manually or using the computer. And how do we go about solving this equation? I'll turn to the next page and show you how that's done. The first thing we do is to write the auxiliary equation or the characteristic equation. And that's how this equation looks in this case here. And as you can see, it's a quadratic equation, which means there are two solutions for s. S is the variable that we're solving this equation. It's the unknown that we're solving this equation for. There's always two solutions, but we do have what you could say two cases. The first case is that we have two distinct roots, so that means the two roots s1 and s2 are not the same number. In that case, we can write the solution as a linear combination of these two solutions, these two exponentials. Each of those exponentials are solutions to the differential equation, but the general solution is a linear combination, C1 times one solution plus C2 times the other solution. So that's the general solution. And we might want to differentiate between two cases here as well. One case is if S1 and S2 are real numbers. So S1 and S2 are real numbers, and that means that the solution, well, that's just a boring exponential. Good old exponential that we know. These are just regular real exponential functions. The other case is that S1 and S2 are complex numbers. And in that case, we get an oscillating solution. If they are complex numbers, we can write them in a certain way. Then S1 is equal to a real part, let's call it alpha. and I times an imaginary part, let's call it beta, and S2 would then be the same real part minus that I times that imaginary part. So these two are complex conjugate, and it has to be that way because the original polynomial here has real coefficients. M, P, and K are real numbers. In that case, the possibly complex solutions to this equation will always show up in pairs of conjugates. And the solution can be written as, I'll just use other because they're not necessarily the same, C3 times e to the power of alpha plus I beta t, C4 e to the power of alpha minus I beta t, which can actually be rewritten into something that's easily interpretable. E to the power of alpha t times C, let's call it C5, cosine of beta t plus C6 sine beta t. So this is certainly a solution which oscillates. We know that cosine and sine are oscillating functions. And then we also have an amplitude here which changes exponentially. It might be growing or decaying. That depends on the sign of this alpha, which is the real part of the solutions here to the auxiliary equation. If it's a physical system, physical realizable system, then this would always be negative because we cannot imagine a system that would just explode in violent motions. All right, and then let's get back to the other case where we actually have the same number for both roots. That means we have a double root, and instead of distinguishing between S1 and S2, we will just call it S because it's the same number. And in that case, we'll write our solution as C1 times e to the power of t plus C2 times t times e to the power of S times t. So it's a different solution. We call this solution here, let's use other color, it's the critically damped case or critically damped solution, because that's the solution which will find the neutral position fastest possible. Whereas the exponential is what we call the overdamped case. So the damping is so great that the box will take longer time to retrieve the neutral position. Imagine there's a lot of fluid friction, so if I pull out the box, it will take a long time to go back to neutral position because the oil friction or whatever it is so strong that the box moves slowly back to neutral position. And the last case, you probably guessed it, well, that's the underdamped case, and the box will move back and forth several times before it ends up in the neutral position. And this is kind of what they would look like. The critically damped goes fast down to the neutral position, the overdamped and the underdamped.